So in this video I'm going to go through the last part of ISP DC electricity, so it's going to be task 5, so it's for unit 2 Edexcel physics. So right at the bottom of here we're looking at pages 134 to 143. We're going to be looking at internal resistance and potential dividers. Okay, so it says how we can use lengths of wire or resistors to help us divide potential. So that's the idea of potential dividers. Okay, in terms of the AA style concept, is not part of the spec. Okay, it's to do with the idea of impedance matching and how internal resistance is used in that. It's used in acoustic engineering actually. The idea of is in that situation the load resistance of a circuit is matched to the internal resistance. And if you match those two things perfectly, you get the idea of maximum power being released from the situation. So that's Max Power Theorem, clearly named after Homer Simpson. If you don't get that reference, you should be watching more episodes of Simpsons. So let's go down. So that's not on the Excel spec, remember, that's just an extra point. Watching Simpsons, that's an extra point. So let's get down to ISP, so explaining everything 3, okay, which is going to be going through internal resistance and potential dividers. So we've got the idea of internal resistance, how we can find internal resistance and EMF of a cell using the graph and using equations. And remember, there's certain terms we need to include, so that's internal resistance, EMF or electromotive force, the gradient, the y-intercept, y equals mx plus c, and lost volts. Okay, so let's first sort of draw a simple circuit and get the idea of what internal resistance is actually about. So let's just have a load resistor here. Should have really drawn an ammeter in there. Let's add a voltmeter over here. Okay, so remember there's voltage lost from here. That's little v. There's a large voltage over here, and that's big V, and that's going to be current and the amount of electrical energy converted. So remember we sort of box this off as our internal resistance. The amount of electrical energy, chemical energy converted to electrical energy is known as our EMF. So the EMF is essentially equal to the voltage added to the lost volts. It is the voltage when the current is 0. When the current is 0, there is no lost volts. Okay, so the EMF is the same as the voltage when the current is 0. Let's zoom out slightly. There we go. Right. So when there's no current through the circuit, there is no lost volts, so these two are equal to each other. So we've got a small internal resistance over here, little r, and we've got a big R over here, so big R, little r. Okay, for our resistance, for our load resistance and our internal resistance. So we can split these because we know that voltage is equal to current times resistance. Okay, so voltage is equal to current times load resistance here. That's little v, so that's the lost volts. That must be little r it's involving, so it's current times little r. There we go. Well, we can bracket those up, or factorize them. Okay, there we go. So we've got that in a separate form. Okay, or also we could leave that as V, which are often given, and IR. So that is the most common way in which this equation is written out. So we can do an experiment, and that experiment can allow us to draw a graph which can find the EMF and internal resistance of a power supply. So that experiment is essentially the experiment that's detailed above in the circuit diagram, and the diagram for the graph actually ends up looking like so, where you've got voltage on this axis and current on this axis, and the graph intercepts like that. Well, we want to know what the gradient tells us and what the y-intercept tells us too. So what do those two things tell us? What does M tell us, and what does, that should be C, the y-intercept. So let's get an equation with V and I in it. Okay, so we can rearrange it. Well, the only one that's got V and I in it is this one over here, so we can rearrange it into this format, having V for your y and I for your x. Okay, so let's rearrange that, so you end up with V is equal to the EMF minus IR. Okay, so there's our y-axis, there is our x-axis, there is our plus C, and our M is minus of the internal resistance. So you can see it, tell it's minus is because the gradient is a negative. So y is equal to V, x is equal to I, M, our gradient, is equal to minus R, and C is equal to EMF. So this is our EMF, that value over there, where the current is 0, our voltage tells us the EMF. And the gradient is equal to minus of the internal resistance. So if that was minus 7, our internal resistance would be 7. Brilliant, that's the first part of explaining everything covered. Second part of explaining everything. So describe how a piece of wire or a combination of resistors can be used as a potential divider. That's pretty straightforward. So it's the idea of the ratio of lengths, okay, is equal to the ratio of potential differences. That's because the ratio of length is also equal to the ratio of resistances. So if that's 3 and that's 7, then my voltage is divided in that way. So if that's 3 ohms and that's 7 ohms, okay, and overall I've got 20 volts, then I know that 3 out of my 10 ohms, okay, so 3 out of my 10 3 over 10 ohms, so 3 ohms over 10 ohms multiplied by my 20 volts will tell me how much voltage I'll get across over here. Okay, so voltage for A, so that is equal to, so it's a third essentially of 20, so that's third of 20, which is 6.6 reoccurring. Sorry, just my previous videos finished exporting. 6.6 reoccurring volts. Okay, so the rest must be made up by this part over here, which is 13.3 reoccurring. Okay, so that's how this idea of potential difference works. Okay, well, potential dividers works. So the ratio of voltages is the same as the ratio of resistances. Okay, so I've been through some simple ways of doing that in class with you guys. So let's get stuck straight into our questions. So down over here. Okay, so we've got a question. We've got a circuit diagram over here. It tells us about the rate of conversion of chemical energy in the cell. So clearly you've got the idea of EMF here because they've labelled EMF up here. They've got internal resistance there, external resistance, they've got current flow in the circuit. So use the symbol as a diagram to write a formula for the rate of conversion of chemical energy in the cell. So rate of conversion for chemical energy is going to be related to EMF. The power dissipated in resistor R, so it's the R on the outside, so power dissipated, remember, is P is equal to I squared R, okay? And the power dissipated in R is P is equal to I squared R again, but this time it's little r. Okay, so to show you what I mean by that, I'll show you how they're written in a mark scheme, because they're written nice and clearly. Okay, so E times I, okay, there we go, I squared R and I squared little r. That's straightforward. Okay. Next. So, use these formulas to write an expression for the based on a conservation of energy in the circuit. Okay, so that must mean the energy lost in the circuit, so the power lost in the circuit must be equal to the power gained inside the circuit. Oh, remember, by the way, it says rate of energy conversion, so that's over time. So the reason why it was EI, I don't think I explained that very clearly, is if you think about energy, energy is equal to V times I times T. So energy is equal to V times I times T. Power is equal to energy over time. So therefore that's going to be E times I times T divided by T, so the T's cancel, so that's why this is EI, or EMF I. So if you want to use a formula to write, use these formulas to write an expression for the based on the conservation of energy in the circuit, so the power out of the cell must be equal to the other two powers. So in other words, EMF times by I is equal to I squared R and I squared little r. Okay, so that's that expression over there. So that's just the power that comes out of the cell is equal to the power that's lost in a resistor added to the power that's lost in internal resistance. So the current I in the circuit above is given by the formula I is equal to EMF divided by the combination of two resistors added together. So that's just a rearrangement of one of the expressions I gave you before in the explaining everything. A laboratory EHC supply, so that's a really high voltage supply, that's what was used in class before, or sorry, I've demonstrated in class before, is designed to produce a maximum potential resistance of 5 kiloelectronvolts. So we did that when we were looking at electron diffraction. Give a typical value of the internal resistance of the supply and explain why it's a value. So it's a very high resistance, and as you probably remember from before, it's about a million ohms, it's a mega ohms resistor. And the reason why is so that you have very short current in case of short circuit, so very low current in case of short circuiting. You don't want people to get hurt, so you end up having a very low current in this process. It's a mega ohm resistor, so that the current is low. So I for the circuit is given by rho, so I needs to be as small as possible, so therefore R is very, very large. So you have a very, very large R, so that I is very, very small. Okay, that's the idea that we've got there. Okay, next. Okay, was this the right one? I've skipped a question. No, I haven't. So, student sets up the following circuit using a cell to measure the EMF and internal resistance. Complete the equation for total EMF in terms of other quantities given in the diagram. So, we've got V, I, and R. Okay, so that's just going back to the one before. Just going back to the idea over here. Okay, that idea over here. He measures the current. He measures the current for different values of resistance, and then he plots a graph of R against 1 over I. So it's a different sort of graph to the one we're used to. So it's got different resistances there, and it's got a length there. Okay, the equation for this graph is there. So they've given us the equation for this graph. Show how this equation is derived from the one you've stated above. Right, so we need to go from that, okay, to something that looks a bit like this one above it. Okay, so let's get a separate new sheet of paper out. So we need to go from the equation we had above, which is this one here, to the one that they've stated there. So we need to somehow get rid of our V and get a big R in there, which is pretty straightforward. So that's I R plus I little r. We need to factorise. So I big R plus little r. Okay, and now we need to rearrange for our big R essentially. So let's get rid of the I first. So E over I, or EMF over I, is or epsilon over I is equal to R plus little r, big R plus little r. So now we're going to get the big R by itself, so you move the little r over, and hey presto, we've got the equation that they want. Okay. It's a nice question for a couple of marks, or sorry, for 1 mark. Okay, because the main thing is that substitution is V equals IR. Okay, so use the graph to determine the value of the EMF of the cell show you're working. Right, so we need to look at that equation and figure out which part of its EMF. So the EMF, so our gradient, sorry, our y-axis is R, our x-axis is 1 over I, excellent. Our intercept, okay, is minus R again. Our y-intercept is minus R, so C is minus R again. And M this time is EMF. So let's have a go at that. So figure out the gradient of the graph to figure out the internal resistance. Okay, so you could figure out the gradient of that graph to figure out the internal resistance. So we've got a variation of something close to 30 ohms in this direction and 20 ohms in this direction, 20 amps, sorry, in this direction. So 30 divided by 20 is 3 over 2. So you're looking at about 1.5 volts. Okay, we'll check that in a second. I'm probably slightly off because I'm just doing it by eye rather than using ruler. Okay, but we'll check that in a second. Show that when the external resistance is 5 ohms, the power dissipated in the resistor is about 0.3 volts. Okay, 0.3 watts. Okay, so the power. So when the external resistance is 5 ohms, so we go up over here. We look at our value for 5 ohms. So you get your value for 5. You go across and it's about 4, or is it's going to be more like 5, 6, possibly 6-ish, close to 6, between 5 and 6, about 5.5. Remember your graph, you'll be able to draw a line. Okay, so power is going to be equals to P. P is equal to I squared R. So you should get a value close to the one they're asking for. Let's have a look. I just realised I missed a trick there in terms of milliamps or amps. They are from very large readings of current. Okay, let's have a look. So, right, so derivation, got that one. You got that one there. Gradient 1.5, that's great. So, from the graph, value of 1 over I is equal to R. Yep, so remember that's 1 over, so you do 1 over your answer. That you got for the graph. So mine was about 4.6. That's why the currents are so large. I should have spotted that. So there's a large currents because they're not your amps. That's 1 over the amps. So therefore you end up doing 1 over your 4.5-ish. It says 4 amps. It says over here, yeah. 1 over is 4 amps. So therefore this 0.25 is the actual current. So 0.25 multiplied by, 0.25 squared multiplied by 5 would give you the power. So get your reading off the graph, do 1 over it, and then multiply that by the resistance. Excellent. Next part of that question. Oops, gone too far. Draw a diagram Student repeats the experiment and an identical cell in series. Okay, so we're doubling our internal resistance, we're doubling our EMF. Draw on the graph the result of this experiment. So we're doubling our EMF. So let's look back at what each of the things are. So the EMF is going to be equal to our gradient, so it's going to be twice as steep. Okay, and we're doubling our internal resistance. So the value of this will be twice as far down. So this will be twice as far down and twice as steep. So it would be like this. Excellent. So yeah, that's all from this equation here. So if we doubled our gradient, we've got two identical cells, so doubling the EMF, so that's for doubling the gradient. And we've got two identical cells, so that's got twice as much internal resistance now, so we're doubling the internal resistance. So doubling that C-intercept. It's going to go down, remember, because of a negative value. I think I've gone too far. Yeah. Okay, so use graph A to determine the internal resistance and the EMF of the battery. So this graph A shows the potential difference across a battery with the current supply. Graph B shows how current in a filament lamp varies with the PD across it. So graph A is potential difference against current, and graph B is shows how the current in a filament lamp varies with PD across it. So graph A determines the internal resistance and the EMF of the battery. So you look at the gradient for the internal resistance, remember, and the EMF as the intercept. So it's about 9 for the EMF. That's changed by about 6 divided by 3, so that's going to be about 2 for the internal resistance. Okay, so minus 2 is your gradient, so 2 is your internal resistance. The lamp is connected to a battery to determine the current in the lamp. Okay, so we've got a lamp is connected to the battery. Okay, so we've got a battery, and so there's a battery there. We need to figure out the current is in there, so we know the voltage of this battery is 9 volts, so we can figure out the current from it by looking across. Right, let's get the mark scheme up. Okay, so just like we got before, the value of the gradient is about, so those two values got correct. Yep, so that's what it said about, it was about 2. Right, so we didn't finish C off, let's have a look at that. So not C, I off. Let's get back up to that. Not that one. I should really look at page numbers. Not that one. Oh yeah, this one over there. The lamp is connected to the battery, connect the, so right, so determine the current across the lamp. Oh right, okay, let's do this correctly, sorry. It's where they cross, because if the battery is connected across the cell, they're going to have the equal voltage across them, so it's where they cross. That's over here, so it's going to be about 1.7, as it said in the, so 2.17, sorry, as it's in the mark scheme, so about over here is where they cross. So that's when it's connected across the battery, the voltage in each will be the same. Sorry, I missed that trick. So it's where the voltage is the same. When they're connected into each other, the voltage across each is the same, because remember they're technically is part of the circuit, same circuit. So whatever's given out by the battery is being used by the resistor. So where they cross is that value of the is the value of current. So calculate the resistance of a filament lamp when it is connected across the battery. So we want the resistance of this filament lamp when it's connected across the battery. So we know the value of this current, which is about 2.2, as I was saying. We can read across the voltage on that, which is about 5, between 4 and 5, and which divide voltage by current to give us a resistance. So if we check on the mark scheme, that's all they're doing for that one. Let's go further down. Okay, so yep, there we go. So it's a rearrangement of V equals IR. So you end up with doing about 2 divided by 2.2. There you go. So you end up with you end up with 4ish divided by 2. So you end up with about 2.1, 2.2. Brilliant. Next, draw a circuit diagram that would enable graph A to be plotted. Okay, so graph A, we know what these look like. These internal resistance diagrams. And they're investigating a filament lamp, so it needs to be a filament lamp here. Okay, and the voltmeter, it could be across over here, or it could be across this, whichever, and the ammeter needs to be in series with the circuit. It's pretty straightforward. Describe how we'd use this circuit to obtain the graph of data. So actually the main thing you really need to get in there as well, which I didn't include earlier on, is some way of varying the power supply or the resistance. You've got needs a variable resistor to vary the current is the main thing there. Okay. So if you look at the next question, 17a, same question, same piece of equipment, same question. Remember, this is your variable resistor this time around. So you just connect it in the same way, you just draw it in the same way. Sketch the shape of the graph you'd expect to see. So this is, oh no, sorry, this is investigating how the filament lamp varies with potential difference, okay? So actually, technically, it's exactly the same setup, except the voltmeter this time for 17a would be across the filament lamp. So there you go, there I am rushing ahead. I shouldn't do that. So you can see the graph, hold on, let me just get down there so you can see it. So voltmeter over there and the voltage across it, like so. And that was the diagram before where I scribbled out the voltmeter for the internal resistance question that you probably didn't see because I didn't have the sheet high enough. So sketch the graph, so remember it would curve like this, went through this in the last video. It would curve like this, and then we're asked to explain the shape of the graph. We've done it before, oops daisy, done it before, so remember it's going to be as the current gets high, the resistance increases due to an increase in temperature, which means it can't increase as much and is therefore limited. And that is the end of the questions on task 5. Let's just double check the last part of these. Right, there we go. So potentiometer circuit is a potentiometer circuit, ammeter in series, voltmeter in parallel, just like we said. Okay, so you've got the curves in each of the quadrants as they're mentioning there. And they've got the idea of the shape of the graph. As the current increases, the temperature of the lamp increases because the lamp heats up, which means the resistance increases, so the rate of increase of current decreases. Okay, so that's pretty much how that works. Now, it does say there's another, in the mark scheme, there's another part of the question, but I'm pretty sure I didn't include it. 422, I'm not sure what that's after. Maybe I've skipped a bit off by accident. So just ignore this last little bit of the mark scheme here. It seems like I've added a bit extra by accident. Yes, taken up to 9 marks for some reason. Not sure what that bit is there. So thank you very much for watching, guys, and I hope you enjoyed the topic of DC electricity. It does crop up again in Unit 4 where we do a bit more work on capacitors and other electrical components, but this is a good ISP for grounding your work in A2 physics. If you struggle with physics, then make sure you look over this again before doing Unit 4, as it will remind you of all the basic circuit rules you need for DC electricity. Thank you very much, guys.